So, hi everyone, welcome back. Today might be the longest tutorial. So today is also quite important where we cover the basics of your SVM. We are going to cover about duality, how we can convert the SVM to a dual problem, and why do we need to convert it to the dual problem in the first place, as well as some beautiful conditions about our dual problem. Okay, so just to give a quick disclaimer, some of the approaches that I'm using here, especially when we formulate the SVM, is a bit different from the lecture. Because I think when I saw the lecture is more into like, I give you the claim, then I prove. I give you the claim, then I prove. So what I'm trying to show here is from building the ground up, right? How do you end up getting that inequality? So the approach might be slightly different. Just to give a quick disclaimer here. But I try to match the notation as much as possible with what Prof. Harold has. Although the notation that I prepared might be a bit different from the solutions because I try to keep it consistent with the lecture instead of with the solution. So you can just to proceed with caution. Okay. So I won't be covering the first few parts because the first few parts is essentially the summary of what we are going to do today. So today we are going to essentially see the optimization problem, see why we can actually use the dual problem to solve SVM and why we need it, and finally to see when does the complementary slackness and KKT holds and how does it infer about the optimality. Okay, so let's just do a very quick recap on what we have seen. We have seen this form of the optimization problem. This optimization problem is what we call the standard form of the optimization problem. So when we say standard form is where we want to always minimize the function. Okay, f0 is what we call the objective function. Subject to these are the inequality constraints. Note that the inequality constraints must be less than equal to 0. So on the right hand side must be equal to 0. Then these are basically our equality constraints. Okay. For the purpose of this tutorial, since we are using a lot of n values also, I'm going to do a slight notation change. Let me denote p as how many equality constraints are present. Okay. So just slight notation change for my tutorial today. Else there will be too many n's. I don't want to confuse you with so many n. Okay. So this is the optimization problem in the standard form. I'm also going to introduce some other notation here. So basically we would denote this x star. X star is essentially just another factor, right? Because your x is bolded, so your x is also a factor. What we denote by x star is essentially what we call the optimal point. Okay, so the optimal point is essentially the value of x, the factor x that will minimize this whole thing. Okay, so that is the optimal point. Whereas for the p star is what we call, this is the optimal value. Okay, why do we use p? P is to denote that this is part of the primal problem. Okay, we will see later on what do we mean by primal and what we mean by dual. Okay, so this is basically the optimal value subject to the constraints. This is important to note. So it is not necessarily the value that will minimize the whole function globally, but it's that given these constraints, your fi and also your gi, what would be the optimal value when you minimize this subject to the constraints? So it might not be the global minimum, but it will be the minimum subject to these constraints. That is our p star. Okay, so if you want to define it more formally, you will see that your p star is essentially what we call, this is your infimum. Okay, so I'm not sure if you tried to Google this, but there's a slight difference between your infimum function and also your infimum operator and your minimum operator. The slight difference is that if I find, say for example, minimum, let's say that my set is some kind of this interval. So it's any real number between 0 and 1, but not including 0 and 1. If I want to find the minimum of this, the minimum element inside this set, I will not be able to find. Because 0 is not included, right? So that I can always find any value that will be so close to 0. Okay? So that means that I cannot just give you a minimum value because simply there's no minimum value in that set. But I can derive what we call the infimum. So the infimum is essentially what is the largest possible lower bound. That is basically the difference. The infimum doesn't have to be part of the set. Okay? But this one is very minor. For now, we can assume that it is essentially doing the same thing as your minimum function. Okay, so this p star is actually defined as what is the value of x that would essentially minimize this entire f0 subject to whatever constraints that we provided here for all I in 1 to m. as well as for all the equality constraints that we provided. Okay, so this is how I would define what is our P star, instead of simply minimizing the entire function. Any questions to this point? Okay, so whenever you see a P star, note that this is essentially the optimal value to the original problem, subject to the constraints. Then whatever X star you see, this is essentially what is the value of X that will give this P star. Or rather, I can also say that P star is essentially the value of F0 of X star. Okay, just some notation thing. So now let's move on to the first problem. By the way, if you have any questions, feel free to raise up, because a lot of math today. Okay, so just raise up any time. So first problem, we want to derive what is the SVM primal problem. What do we mean by the primal problem? Primal is essentially just the original problem. So if you want to formulate SVM as an optimization problem, how would you derive the problem? That's essentially the purpose of this question. So we want to find the standard form. Then we want to identify what is the objective function, what do we minimize against, as well as the constraints. Okay, so let's try to see what we are trying to do with an SVM. So let me try to draw a simple thing from scratch. Okay, can someone tell me what is the purpose of an SVM? What are we trying to do here? SVM. Say for example, I have these are my positive data points, then these are like kind of my negative data points. What are we trying to do? Are we trying to draw a line? SVM? What is our goal in the SVM? So if I want to simply draw a line like this, right, then I will separate it out. This part is simply your logistic regression, right? Okay, this part is simply your logistic regression. So we want to do something a bit better than this. What we want now, or maybe something like this also. This is a valid logistic regression result. But if you want to do it intuitively, if I want to separate this out, right, then I want to some kind of putting that this line might be a better choice. Why is this line a better choice? Because it separates the gap between the first negative example you see with the first positive sample you see. I want to maximize this gap. Okay, so that is what we call as the margin. Okay, so that is why I will have to write this first. SVM is essentially what we call a maximal margin classifier. Okay, this popped out in the true or false question for the past two past year papers. Okay, so SVM is what we call the maximal margin classifier, because you want to classify things but you want to maximize this whole margin. You want to make sure that the gap between the first positive sample and the first negative sample you see is as wide as possible. So if I try to imagine this, right, you can see that this will look something like a highway kind of thing, or gutter or longkang, whatever you think is it. Okay, so I can draw it something like this. Okay, so you can see that it's kind of like a street or a gutter. Okay, where this is where I will hit the first negative sample. This is where I will hit the first positive sample. My goal is that I want to maximize what is this margin. Okay, for this problem, what I will show also is how to maximize the width, which is just 2 times the margin. Okay, so this is basically the concept of a gutter that we have. Now I will start to introduce some factors here. First thing, we would denote 2 factors. First is the factor W. This factor W is essentially what is a factor that is perpendicular to the decision boundary. Okay, so this is, I mean, if you want the technical term, this should be an orthogonal factor to whatever hyperplane that is cutting our decision boundary here. You can see it like this. If this is my decision boundary, basically my orange line, then my W will look something like this. So it doesn't have to be the exact length of the entire margin, but as long as it is perpendicular to our decision factor, this is okay. Okay, so this is how I define my W. Any questions? No? Okay. Then I will define another factor. Another factor that I will define is essentially just any factor U. So U can be simply any point inside my entire Cartesian plane. Okay, I can set any point U, then this will be basically just a position factor to that point. Okay, so this is my U. So U is just any unknown factor, which for now you can think of it like some kind of a position factor. Okay. So with this, then I will establish some kind of connection to determine whether if I give you a sample U, is this positive or is this negative? That's my goal. Okay. So let's see. If I try to set this with a certain decision boundary, right? My decision boundary for now, I will set this as the orange line first. Okay. For now, this will be at the orange line. If it's above the orange line, this will be positive. If it's below the orange line, this will be negative. But I want you to imagine this way. If my U is long enough, right? If my U is further long, then I want this to be positive. If my U is shorter, then I want this to be negative. But in terms of what? I can set a U that is very long, but then it will go very here, right? Okay? Then the length of U itself cannot be the decision, cannot set our decision of whether this will be positive or negative. But we want to determine what is the length of this U with respect to this W. Okay? I want to determine what's the length of this U with respect to the W to see how far I'm actually going from the position 0 to reaching the decision boundary. So this W is for me to calibrate what is the length of this U with respect to heading towards the decision boundary. Okay? So the logic is this. If this length, my projection from U to W, is long enough exceeding the decision boundary, then this will be positive. If this is low enough, then this will be negative. Okay? So when I talk about projection, then that is where we will introduce this concept called a dot product. Okay? So note that dot product is essentially if I take, say for example, this is my factor A, this is my factor B. Okay? If I do A dot B, or maybe I do something that is shorter here. So if my A happens to be a bit shorter, let's say my A is like this. Okay? Then when I do A dot B, you know this from JC formulas, this is essentially what is the magnitude of A times magnitude of B times what is the cosine of the angle between. Okay? If I just take this A cosine theta will actually tell you what is the length of just this segment. This is basically your A cosine theta times what is the length of this B. In essence, your dot product is telling you the product of this length with this length. Okay? That is your dot product. So actually, if I want to just get what is this length, then I'll just divide by whatever value of B is. Okay? But here what I need is just essentially a comparison. Comparing between, say for example, I have this is a shorter U versus this is a longer U. If I take the length with respect to W, whether it will exceed my decision boundary or not. Okay? Since my W will stay fixed here, I define W as a factor that's perpendicular to this decision boundary. It will stay fixed. Then I don't have to essentially divide with the magnitude for now. Because all I need to do is to just quickly compute how do I compare between the first U and the second U. Okay? Questions on this? On why we need to use the dot product? Okay. So with this, then I will establish our dot product property here. My decision boundary is now, I want to determine, given any value of unknown factor, I want to find what is the dot product with this W and see whether it exceeds a constant or not. Okay? Or if I try to make it in a form where my right hand side is 0, then I can shift this C around to my left side. Let me just call this B for now. So I can say this can be something like this. Okay? Where B and C are just constants normally. If I shift the C to the left side, then B is equal to negative C and that's it. Okay? So this is now my decision boundary. If I take a factor, I dot product with W, I plus B. If it is greater than equal to 0, then I will set U to be a positive sample. So I take a point U. If I dot product plus B, if this is greater than equal to 0, I will set this as a positive sample. If it's less than 0, then I would set this as a negative sample. Okay? Any questions? Okay. So now I will establish a further item here. Let me try to make this margin a bit bigger. So saying that I don't want to classify them falling between this boundary, but I want it to classify after I hit these boundaries. Okay? So I want to determine such that when I have this line, the top line there is basically my first positive sample. Bottom line is my first negative sample. Okay? So I will redefine this decision boundary. I can have this thing. say for example, if I take any positive value of x, okay? If I take any positive sample of x, I do a dot product, I do plus b, I want this to be greater than equal to 1. If I do this dot product on a negative case, then I want this to be negative 1. Okay? This is essentially your sign function that Prof introduced. So this is going to be basically the margins of my whole classifier here. Essentially, if I take any positive case, I want this to be exceeding 1. If I take any negative case, I want it to be below negative 1. That is what I'm trying to do here. Okay? Any questions so far? But hey, you see now that I will have to maintain two different inequalities, which is a bit troublesome. Can I combine them into one single inequality? That is where we start to introduce a new constant, which we multiply them by what is the target. Okay? So we define the target here. This part is essentially what is the sign function. That means I will take this target is equal to 1 if my x is a positive case. This target will be negative 1 otherwise. Okay? So with this, if I multiply them, I will just get this value where I'm saying that Tn, if I multiply by what is this wx plus b, this will be greater than equal to 1. Okay? Solely because if I put this here, right, then this will be just multiplying by a negative 1 value. If I multiply this by a negative 1, then I can just divide by another negative 1, then this sign will flip, this will be 1. Okay? So essentially, these are just the same item. Instead of differentiating our x by x plus and x minus, I will say that I can just take any value of x, then I specify my Tn, which depends on what is the xn value here. If my xn is positive, then Tn is 1. If my xn is negative, then Tn is negative 1. Okay? Questions? So noting this point, this is essentially my, I will just circle this first. This is an important inequality which you will see later. So once I have this, I can also set another thing. This is basically the entire classification I want to have, right? So that means that if it happens that my xn falls inside my gutter, okay, if this is my kind of like my longkang, right? This is my gutter. If my x falls within that boundary, if it falls within that boundary, then this inequality must be what we call active. When we say this is active, then I will have, this will now become what we call an equality already. Okay? So any value that is outside of this highway, outside of this gutter, right, this will be greater than equal to 1. But the moment that it hits this gutter, it should be equal to 1 because I want to determine the size of this gutter first. Okay? So if this xn touches the gutter, I will set this equal to 1. Any questions? Okay, once this is established, then now we can just simply do the fun part. Now we want to find what is the width of this entire gutter. Okay, how do we find the width? Let's see here. If I take, this is my initial gutter here. Let me just draw the gutter. So I think this will be like kind of my negative case. This is kind of my positive case. Okay. Let me define two factors again. This is basically the factor x minus that will hit the that will hit the gutter in the lower half. Then this will be the factor that will hit the gutter in the upper half. Okay. So these are basically my first positive case, my first negative case. The moment this happens, then I want to find what is the width of this entire gutter. To do that, I will need to find what is this factor first. This factor is essentially my positive x minus my negative x. Position of x plus minus position of x minus. Okay? This is essentially this factor. If I want to find the width of this margin, then all I need to do is to just find what is the projection, what is the length of this projection with respect to whatever w here is. Okay? We define that w is the factor that is perpendicular to our margin, right? Okay? So if I want to find what is the length of this margin, I will just need to see if I project this factor x plus minus x minus, right? If I project it against this part, what is the length of that factor? That is what I'm trying to do here. Okay? So then I want to find the projection. To find the projection, then I can just simply put in the formula here. This is my initial factor. I'm going to do a dot product with W. But if I'm concerned with the length of the projection, then that is where I will actually, instead of doing a dot product with W, I will have to do a dot product with whatever unit factor of W. Okay? Because just now remember that when I do dot product, it's basically the length of this factor times length of W times the cosine theta. But if I'm concerned about what is just the length of this projection, then I will have to divide it again by the magnitude of W to get what is magnitude of this cosine theta. That's my goal. Any questions? Yeah. So from this thing, I can actually already derive what is my x plus and also x minus here. So let's take if this is x plus. In the case that this is x plus, then Tn will be positive 1. So now I will have w dot x plus b is equal to 1. Or I can say that w dot x for a positive case, this will be equal to 1 minus b. Same goes if this is negative, then I will have negative of w dot x plus b is equal to 1. So I will just shift the b to the right side, then this will be negative of w dot x. This will be 1 plus b. Okay? So this is what I'm trying to do. The moment I have this, then I can just do a dot product. You can see the properties later on. But x plus dot w, this one, the dot product, I can actually expand. Minus x minus dot w. Okay? Then I will divide everything by what is the w. So when this happens, then I can just plug in the values. This was 1 minus b. Then the top one was 1 plus b over w. Then I will have the entire width is essentially just this thing. So the entire width is essentially 2 times 1 over magnitude of w. So 1 over magnitude of w is essentially what is the margin from the decision boundary to this point. This is the margin, your 1 over w. Whereas the entire width that I'm concerned here is 2 over this thing. So when we formulate this as a maximal margin classifier, we want to determine what is the value that will maximize this thing. Any questions? Okay, you can check this later on. So basically, we want to find what is the value that will maximize your width or your margin. The same thing. Okay, so then this will be where the magic will happen. Since it's a constant, I can drop them down. So this will be just maximizing my fraction. Which, maximizing this fraction is equal to saying I'm minimizing whatever is below in the denominator side. So I'm converting my maximization problem now to a minimization problem. The moment this minimization problem is handled, then next thing I want to do is to just do this part. Note that this thing is just for mathematical convenience, because your magnitude is defined as what is the square root of w1 squared plus w2 squared, so on and so forth. Okay? So for mathematical convenience, I'm going to square that so I don't have to handle with whatever square root is present. Then this half is so that when I differentiate it, it will cancel. So it's for mathematical convenience. Any questions? Now once we have this, then we can already formulate what is our primal problem. So our primal problem now is essentially, I want to find the value of w as well as b that will minimize my 1/2 magnitude of w squared. Subject to what constraints? We have some constraints here. The constraint now is that when I want to maximize this margin, okay, I want to ensure that any positive case is above this margin, any negative case is below this margin for any values of x. So then that is where my decision boundary here will come in. This is my decision boundary. So this should hold true for any value of x. So whenever I put the target with, this is basically the value that I'm concerned with, this must correctly classify for positive cases and for negative cases. Any questions? So you notice that this part is just the normal primal problem. It hasn't followed our standard form. So to follow the standard form, that is where we have to set this less than equal to 0. Then all I need to do is to just move my Tn to the right side. So with this, I can just come up with, this will be such that 1 minus Tn, this will be less than equal to 0. Now I have my problem in standard form. Any questions? Okay, I need to put another item here. I will say that this is for every single n ranging from 1 to capital N. What this means is essentially I need to make sure that this constraint is satisfied for every single sample that is in my dataset. It cannot violate this thing. Okay? Note that this is just a hard margin SVM. We assume that the data is linearly separable. When we assume that it cannot be separated, that is where you go to problem 2. Okay? Any questions? Okay, if no questions, now we already seen what is the primal problem. We also seen what is this P star, which is the optimal value. Now, for any given optimization problem, we can now utilize what we call the Lagrangian. Remember that last week we discussed about Lagrangian multipliers. That is, for every single equality, I can just multiply each of them by the Lagrangian multiplier. Okay, so we actually apply something similar here. We can arrive at what we call the Lagrangian function. This is essentially saying I'm multiplying the multiplier to every single constraint. For any inequality constraint, I multiply by this lambda. For any equality constraint, I multiply by this nu. Okay? Why do we separate this? We will see this later on. There's a specific meaning for each. Okay? Any questions? So essentially, we just multiply this by lambda. We multiply this by nu. So this lambda is what we call your Lagrangian multiplier that is associated to the inequality constraint. Whereas your nu, this one is your Lagrangian multiplier associated to the equality constraint. So this lambda and nu, these are what we call the Lagrangian multipliers, whereas the factors, these are basically the Lagrange multiplier factors. Okay, so these factors will in the end form what we call our dual variables. Questions? This will be our dual variables. So this is where I will introduce another terminology. You will see there is going to be this other function. This is different from your normal Lagrangian. This is what we call the Lagrange dual function. Why is it called a dual function? Because it is only related to the dual variables, which is your lambda and your nu. Okay? It's called a dual function because you only want it to be associated to the dual variables, lambda and nu. What it does is essentially, this is your Lagrangian dual. It's trying to see for every single possible value of your x. I want to determine what is the lower bound of this Lx lambda nu. Basically the lower bound of our Lagrangian function. So this function, we take what is the lowest possible bound given all values of x. Then this is our Lagrangian dual. Okay? Any questions? Okay. Yeah. So we try to see how we can write the Lagrangian and the Lagrange dual for this SVM primal. Just now we've seen that this SVM primal is essentially I want to minimize this function subject to this constraint. Okay? So notice that this part will now become my objective function. This part now becomes my inequality constraints. Then I will not have any equality constraints here. Because there's no gix equals to 0, right? All of them are inequality constraints. So when I want to construct my Lagrangian dual and my Lagrangian function, I can say this is a function of connecting my w and also the b. Because just now when we did this, I want to minimize against these two. Okay? So I will still have to utilize both w and b. Then I will only associate it with the lambda factor. Because there are no equality constraints. So I don't have to associate it with nu. Okay? So I can define it this way. I can just write, this is my objective function. My objective function is simply my 1/2 w squared. Then I will do this is plus. What is the sum from all, let's call this from n equals to 1 up to capital N, for every single inequality constraint that is there. So the inequality constraint must be satisfied for every single sample, right? That's why I will loop through from n equals to 1 up to capital N. I will multiply, this is my, this would be lambda times lambda n, multiplied by whatever the value of the fi is. So this will be 1 minus tn w dot xn plus b. Okay, just to reiterate, this is our objective function. This is our inequality constraint. Okay, so similar thing as what we seen last week. Any questions? This is just the Lagrangian. Okay, so when we want to derive what is the Lagrangian dual, the Lagrangian dual now, it should no longer depend on my w as well as my b. It should only depend on what is the lambda value. So with this, then I will derive my Lagrangian dual. This is my Lagrangian dual that depends only on the lambda. This is just taking what is the lower bound with respect to any possible value of this w and b. We want to minimize this Lagrangian function. Okay, questions? So when I want to minimize this Lagrangian function, what will come to mind if I want to minimize this with respect to w and b? And for this point, you should already know that you have to use derivatives. Okay, so to formulate this Lagrangian dual from this Lagrangian function, we will take the derivative with respect to whatever variables you are trying to minimize here. Okay, so when I take the derivative, I will have two new constraints here. My first constraint is I want to set this to be equal to 0. It should be equal to 0. Okay, this is my first item. My second item is when I take the partial L, capital L over partial B, this should also be 0. This is my goal. Okay, so now let's see for the first one first. So the first one, I can actually rewrite this in terms of just normal multiplication. So this will be easier to see. Now this will be just 1/2 of sum of every single possible wi squared, where I define, say for example, if my w is like a factor that will depend on dimension d, then I can just put it this way, plus the sum of I equals from n equals to 1, capital N, lambda n. So I'm trying to expand the bracket here. Then I'll do a minus this thing. This is I equals to 1 up to capital D, lambda n, tn, w, I. Then this will be xni. Then this will be minus sum from every single n, lambda n, t, and b. Okay, this one I just expand the bracket. Now I can find what is my partial L over partial 1 single wi. Then this one I no longer need to demonstrate how to do the partial. I've been demonstrating for how many weeks. So this one is just simply you differentiate this. Now you will get this will be wi minus sum over all possible n, lambda n, tn, xni. Okay, this is my partial L over partial wi. So if I want to find what is the gradient function, the gradient function now is just basically a factor of this. So if I convert this back into the factor, you will see that this will now be w minus sum of all n's, lambda n, tn, and the factor xn. Because here xni is essentially what is the, given my factor xn, I want to access which element. So if I make this an entire factor, now this will be, this is my all of w, all of xn. Okay? So that is essentially what I want you to think for now. Then I want to set this gradient factor to be equal to 0. Thus, from here, I will obtain my first inequality, and my first equality that tells me that this w, when it is in the optimal value, this should be equal to lambda n, tn, xn. Okay? This is my first constraint. My first constraint is when I minimize the Lagrangian function with respect to w, w will be equal to lambda n, tn, xn. Any questions? This is my first constraint. My second constraint is obtained when I differentiate L with respect to B. When I do that now, and I set this to be equal to 0, notice that the only term containing B is here. So when I differentiate with respect to B, now this will just be saying that this will be n equals to 1 to capital N, lambda n, tn is equal to 0. So now this is my second constraint. My second constraint is telling me that when I minimize this problem, okay, when I try to get what is the value that minimizes this Lagrangian, this constraint must be satisfied as well. So I can actually substitute these values back to the original Lagrangian. I substitute back here. So I can say this is my L W B lambda, just putting back whatever it has been provided here. Lambda n, 1 minus Tn, W dot Xn plus B. Okay, so substituting here, I can just rewrite this W squared. We can utilize the common property here. This is just basically a W transpose W. Okay, when you want to find the square, basically the square of the magnitude is just the dot product. So essentially just W multiplied by itself. Okay, so the moment that happens, then I can just plug in this value. This is my W times W, so it's just this thing. Transpose, then I'll put the same summation. Plus, now this entire sum I can also expand. This will be the lambda n, minus this is the sum from n equals to 1, Tn, lambda n. Let me put this as m instead, so it's easier to see. Okay, so I can differentiate what is the first n versus the second m. Okay, both of them are still reaching capital N. Okay, so then I will have this is my Tn lambda n. Then I'll multiply this again by whatever value of the W. This is quite tedious. Then multiply by Xn, by this one. Okay, then finally there's a minus B sum of from n equals to 1 up to capital N lambda n Tn. Okay, so you will notice that when this is in its optimum value, right, this part will actually be 0. Okay, because of the constraint that we have set. But then again, this is just the constraint when it is minimized. It may be possible that it is not minimized, then I can actually get a very unbounded amount. Because the moment that this is not equal to 0, I can always find a very, very, very large amount of B that will make this function all the way down. Okay? See, the moment this is not equal to 0, I can always find a large enough B that I will cause this whole function to be dragged down by this negative B sum of this thing. Okay? So that means that at the optimal value, my Lagrangian dual now will actually be some kind of a piecewise function. Okay? This will be a piecewise function that tells me that this will be actually unbounded the moment that the constraint is not satisfied. But when the constraint is satisfied, this will have a certain value. Okay, so there's a constraint that I need to satisfy here. If I don't satisfy this, then I can always find a large enough B that will cause this whole function to go south. Any questions? Yeah. Then all you need to do is to just expand this, which I will not demonstrate now because I don't have enough time. But when you expand, now you will have basically this thing. This will just be your lambda n minus this is your 1/2 sum from n equals to 1, sum from m equals to 1. This is your lambda n, lambda m, Tn, Tm. This will be your Xn transpose Xm. Okay? So this is basically our Lagrangian dual. Our Lagrangian dual is saying that, hey, I will arrive to this value if this constraint is satisfied, negative infinity otherwise. Okay? So that's our Lagrangian dual. Any questions? Questions? No? Okay. So actually I have a very quick detour on explaining dual problem, but I don't have enough time for now. So maybe I'll just cover this as a recording later on. But for now, I want to cover the last few parts because that one is more important. So once we already arrived to a Lagrangian dual, what we have now is essentially we can utilize what we call the dual problem. So dual problem is essentially, if the original problem is too hard for me to solve, I can formulate another set of the problem that can be easier to solve, and this will be some kind of a bound to my original problem. Okay? So this will serve as a bound to my original problem. What it does is, it will take my Lagrangian dual, it will maximize whatever lambda and, we will find whatever lambda and nu to maximize the Lagrangian dual. Subject to your lambda must be greater than equal to 0. So you might be wondering, why must this be true? This is because we want to maintain one property which we call the weak duality, or what we also call the lower bound property. What we are saying is that we want to determine such that this Lagrangian dual happens to be a lower bound for my P star, for my original problem. So whatever I find here as my maximum value, this should be less than equal to my original P star for it to be an actual bound. Okay, so for it to be an actual bound, I want to have such that every single lambda should be greater than equal to 0. So why is this so? I can show very quick here. Essentially, at the start, you will notice that we have this thing. This is our lambda I fi of x, plus this is our nu I, and then gi x. Okay? Initially, we will add this to our Lagrangian. Notice that when our x itself is a feasible solution, when we say feasible, it means just a valid solution that satisfies the constraints. When this satisfies the constraints, this fi will be less than equal to 0. This gi will be equal to 0. Okay? Essentially saying, this whole part is actually 0. The moment that our x itself is feasible. Okay? When x is valid, then this whole part is 0. Then I just need to focus on this thing. For me to ensure that this will be a lower bound, I can just put, say for example, this will be an inequality constraint. Then this will be, say, I will add what is the value of FO. This will be the value of FO also. Notice that this is basically our primal problem, the primal objective. This whole thing is our Lagrangian function. Okay? The moment this adds on, it will only tell me that this will only be satisfied when this whole thing is less than equal to 0. Okay? So this whole inequality is satisfied when this part is less than equal to 0. The moment this is less than equal to 0, then I notice that my f is always less than equal to 0. Then I just need to ensure that my lambda is always a positive value, such that this will be, when I multiply this positive constant to a negative value, this will be always a negative value. That's why this will be always less than equal to 0. Okay? So the important part here is that when you have a Lagrangian dual, if you want to formulate the dual problem, any Lagrange multiplier associated with the inequality must be greater than equal to 0 for us to satisfy the lower bound property. Okay? Yeah. So that is essentially the goal of this thing. Now we want to write what is the SVM dual. So the SVM dual is essentially just put in the template here. We put the Lagrangian dual, which is basically our n equals to 1, lambda n minus whatever this value is. Lambda n, lambda m, tn, tm, xn, xm. Okay? So this is our Lagrangian dual. We want to maximize this subject to each lambda must be greater than equal to 0, as well as, remember that just now we have one constraint that will make this bounded. That is, your lambda n tn must be equal to 0. This is from your partial L over partial B must be equal to 0. Okay? Any questions? So this is our SVM dual problem. Now one thing you should notice at this point is that this part is essentially just the dot product of xn and xm. The moment we formulate this dual problem, we no longer have to find what is the value that will minimize the W. As long as I can find what is the dot product of all possible pairs, right, then I can actually maximize this. In fact, if you go to the original decision problem, the original decision problem will tell us that this W dot U plus B will be greater than equal to, say, 1, right? Okay, this is our original decision problem. So the moment I substitute the actual W we have seen, lambda n tn xn dot u plus b greater than equal to 1. Now notice that at this point, we can actually just compute this based on taking the dot product of that new position with respect to any pairs that we have seen just now, with respect to every single xn we have seen. So now your SVM no longer depends on a value of w that you find, but now it just depends on what is the x with regards to whatever Lagrangian multiplier you set. Okay? Questions? Okay. Now, note that when we have your optimal dual value, we denote this as D star. That's why we denote just now P star as your optimal value for the primal problem, D star as the optimal value for the dual problem. Okay? So when we have your D star is less than equal to your P star, when this is a lower bound, we call this a weak duality. Whereas if this is equal, then that is what we call a strong duality. Okay? So just note, weak duality is when D star is a lower bound. The moment that this hits equality, that is what we call the strong duality. So weak duality is, this one is commonly holding, regardless of what type of function f0 is. But your strong duality only works under certain conditions. So we want to see here, if we try to assume that your strong duality holds, okay? If we try to assume that this thing holds, we want to see what kind of condition we can have. So now we set x star to be the primal optimal, lambda star and nu star to be your dual optimal. So if we assume that this strong duality holds, I can have my p star is equal to d star, such that p star is initially my f0 x star, right? Okay, this will be equal to whatever the value of the Lagrangian dual is. I'll just omit the arrow for now. Which, this is essentially taking the minimum of the entire Lagrangian. This is your f0x plus your sum of lambda I star fi x plus sum of nu I gi x. Okay? This whole thing, since I'm taking this is the lower bound, right? That means for any value of x, this will be greater than equal to the lower bound. Okay? So this would be, I can take, say for example, if I substitute this x by x star, I know that this x star value for the Lagrangian function will be greater than equal to whatever the lower bound we have found. Okay, so I will put this will be my f0 x star plus this the sum plus sum of nu I gi x star. Now I notice that this thing would be less than equal to my fx star. This is by weak duality. Because I noticed that, if I have, this is my Lagrangian function, right? My Lagrangian function will always be less than equal to whatever the original problem is. That is our weak duality. So notice that this is greater than equal to my f0 x star and will be less than equal to my f0 x star. Which can only mean that my f0 x star will be equal to this thing. Okay? Any questions? This is a long thing. Okay? This can only be equal to this. And thus, this will be cancelled out, right? So this will be 0. But you notice that if x star is an actual solution, it will satisfy the constraint that this part, gix, will be equal to 0 also. So this whole thing will be 0 also. Then that means this will only leave us out with one thing. Lambda I star fi x star is equal to 0 for all sum of this thing. Any questions? Now notice another thing again. Just now we have shown that this thing will always be less than equal to 0, right? Then we know that this part is always greater than equal to 0. For me to have this sum to be equal to 0, each element here, lambda times f, will be less than equal to 0, right? So for me to have this entire summation to be equal to 0, there cannot be any positive value. So all of them are at least 0 or negative. Then this can only mean one thing, that every single term here must also be equal to 0. Or else this will never reach 0. If one of them is non-zero, it will be negative. There's no positive value to cancel this out. So it must be every single thing is equal to 0. Okay? Moment this happens, this is telling me that at any point in time, it's either that my Lagrange multiplier is equal to 0 or the value of this fi is equal to 0. When this value of fi is equal to 0, that is when we say that the constraint is active because your x is now located at the bound of that constraint. Okay? If my constraint is saying that this is my f is less than equal to 0, then x can be anywhere in the middle, right? But the moment it's equal to 0, my x is exactly at that bound. So I'm saying that the constraint is active. Okay? So this is telling me that my x can only be either at that bound or my Lagrange multiplier has to be 0. Any questions so far? Okay? So x can only be at that bound or the Lagrange multiplier has to be 0. This is what we call the complementary slackness. Complementary slackness means that either the constraint is active or the multiplier associated with that will be 0. So if we try to relate this with what it is present in the SVM, what we have seen thus far is that in the SVM, our constraint is saying that our constraint is 1 minus Tn of Wxn plus b. This will be less than equal to 0, right? Okay? This is our constraint. So the moment that strong duality holds, the moment that your dual problem optimal value is equal to the primal optimal value, then complementary slackness must hold. Which is saying that either my x has to be at the boundary, or the Lagrange multiplier associated with that constraint will be 0. What it's telling me is that the moment that any value of positive and negative that is outside my boundary, outside of the boundary, the Lagrange multiplier associated with them will be 0. The only time that this will be non-zero is when it has to be at the boundary for, at that point, for the hard margin SVM. Then you have a Lagrange multiplier that can be non-zero. So when this happens, then you know that when you have your entire SVM, the entire Lagrange multiplier will be all 0, 0, 0, 0, except for the one positive case or multiple positive cases, multiple negative cases that are in your boundary. Then they will have the Lagrange multipliers. That's why we call the SVM as a sparse machine. Because now all your multipliers, your parameters here will be zeros. Okay? Any questions so far? Okay, I think I'm running out of time. Maybe for the KKT part, this part I will actually just record it later on because I don't have enough time for this. Okay? Now if you are interested, feel free to ask me more also. This is a very long tutorial. But yeah, please watch the recording later on for the KKT side. Because I think it will be meaningless if I speed run everything in 2 minutes. Okay, so yeah, that's it for today. Please scan the QR code if you haven't. I'll just record KKT.